This video deals with hypothesis testing for proportions. And so just take a minute to press pause and read the scenario of what we're looking at here regarding bomb detective devices. All right, welcome back. And as you see, I've highlighted some of the more important items, and I've gone ahead and taken the liberty of setting up our null and alternative hypothesis. So first, the big thing is they have 4 empty boxes in a room, and only one of the boxes has an explosive at random. And they're going to do this 50 times. So our null hypothesis is that this bomb sniffing device or detective device is no better than chance. So you would have a 1 in 4 chance of getting the correct determination anyway. So that's where I get this p equals 0.25. Now if the device is better than that, if it's convincing enough, then we're only interested in a one-sided test here, only the bomb being better than chance. We have to take a look at our assumptions and conditions, and so we believe that this is a random set of trials. And so, the ability to detect a bomb from one trial to another is independent. I believe that 50 trials is less than 10% of all trials that I could run. And the last piece is the n times p naught. Now, in the confidence interval, it would be about the number of successes that we observe. In this one, out of 50 trials, it would be the number of successes that you would expect to observe and the number of failures that you would expect to see. So we're running off of p naught and 1 minus p naught. And those values are 12.5 and 37.5 respectively, both greater than or equal to 10. So we're good to go, and we're going to run a 1 proportion z test. Now, you know me, I like pictures, and so here's 0.25. That's where I believe my null hypothesis to be. And my p hat is 16 over 50, which gives us 0.32. So we say, well, here's 0.32. And we're interested in this probability of observing that value or higher. So we're going to figure out our z-score. That's going to be 0.32 minus 0.25 over our standard deviation of p hat. Standard deviation this time is denoted, and I'll write it up here, and our standard deviation of p hat, not standard error, is equal to p naught, q naught, or that's 1, where q naught is 1 minus p naught, divided by n. So that's going to be 0.25 times 0.75 all over 50. And for a z-score, we're going to get, or a z-stat, I should say, approximately 1.14. And so what we're looking for is the probability of p hat being greater than 0.32 is the same as the probability of z being greater than 1.14. And I'm going to carry this over onto the next slide. I've taken the liberty of already pre-writing, and again, the same thing that I just had written on the other slide, the probability of observing a sample proportion greater than 32%, given that the null was true, that it's not as effective, is the same as the probability of observing a z-stat greater than 1.14 is equivalent to the calculator charge of, we're going to go to norm CDF and our normal distribution, right? This is a normally distributed variable. And same thing as always, we have a lower bound and upper bound, mu and sigma, and so we have 0.32 as our lower bound, all the way to 10 to the 99, or 1e99, depending on how you like to use your infinity notation or entry. A mu of 25%, and this calculation comes out to be approximately 0.0612. So again, the area over here that's greater than 0.32 is called our p-value, and that p-value is equivalent to 0.13, or 13%. Now, with an alpha value, I would say of 0.01, right? We want something pretty strict so that it's tough to reject. With a p-value of 0.13 greater than alpha of 0.01, we're going to fail to reject. We do not have enough evidence to reject the null hypothesis. We have no reason to believe otherwise, that this machine is no greater in determining a bomb other than pure chance itself. Now, was our test one tail upper, lower tail, or a two-tailed test? Well, it was a one tail upper. And why did we choose that? Because we were only interested in the device working better, right? Or more effective. Explain what your p-value means in context. And here you have it. The interpretation means this, that if the device was really no better than chance itself, we'd expect to see a sample proportion of 32%, approximately 13% of the time. Meaning that even if it is no better than chance itself, it's not going to be exactly 0.25. But how far away from 0.25 would we have to get till it really blows my mind? Well, more than just 13% of the time. I'd have to see something that was, according to our alpha value, 1% of the time or less. If I witness something that I shall only see 1% of the time or less, then I guess what I originally believed about the true proportion was not correct. So, in the end of the day, this is kind of a tough problem, but the bottom line is we don't feel this device is working any better. So, don't invest in it. What I want to do for the next two are just write the null and alternative hypothesis and then go right to the conclusion. And you can look at doing the rest of the work a little bit more in depth on your own. It's important that we have an understanding of how to set up the hypothesis, null and alternative, and make sure that we come to the right conclusion. After reading this on your own, what we're looking to decide is there evidence to support the fact that participation rate by females has increased? Our null hypothesis is going to be that no, it hasn't increased. And so our null is that the proportion of women participation, female participation, is 42%. And increase then, as our alternative, is that P is greater than 0.42. After running the test, you should get a z-stat of 1.076 and a p-value of 0.141, or pretty close depending on how you round. So what should be our conclusion? Again, I think an alpha level of 0.05 would be sufficient on this one. It's not as rigorous as the bomb sniffing device. We're not going to hurt anybody if we're wrong here. Maybe some feelings, I suppose, or maybe some marketing dollars. But we should say something along the lines of, with a p-value of 0.141 greater than an alpha of 0.05, we fail to reject. There is no reason to believe female participation has gone up. And that's it. Take a minute again and read this one on your own. Set up your own null and alternative hypothesis, run the test, come to a conclusion, and match it up with mine. It may be worthy to note that this is slightly different in that the p-hat is already given as 38%. So that's x divided by 801 equals 0.38. After you multiply 0.38 times the 801, you get 304 and change. But remember, this is a number of people, so the authors had rounded off to 305. And if you divide 305 by 801, you're going to get a decimal approximation of 38%. So that's where the p-hat came from. It's handy to know that when we go for the calculator help here. Okay, so I have a pretty busy picture here, and I know it says check the necessary conditions, so we're just going to talk our way through this. First of all, 801 black Americans is less than the population of all black Americans. I believe that there's a random sample of black Americans, and 28% of 801 black Americans is definitely over 10, and 1 minus 0.28 times 801 is definitely over 10. So we'll expect to see out of 801 black Americans over 10 successes and failures. That means 10 people who success, unfortunately, is referring to people who have had trouble affording medical care, and failure is not, which is sort of ironic. So moving on through the test then, we see that we have a z-stat of 6.35 and a p-value of 1.06 times 10 to the negative 10 power, or essentially 0%. I don't want to say 0, but just for space concerns here, that we should almost never see, if it was true that black Americans had the same likelihood of having trouble paying for healthcare as all Americans in general, then we should almost never see the sample that we saw. But we did. And our assumptions and conditions state that we have a pretty reasonable representative sample. So what's our conclusion? Our conclusion is that with a p-value of 1.06 times 10 to the negative 10, less than an alpha of pretty much anything, 0.1 that we would use in this class, we reject the null. It appears that black Americans do have a more severe problem in terms of affording health care. It just dawned on me that I don't think I originally talked out my null and alternative. My null was that the percentage of black Americans affording health insurance or medical care was 28%, and the alternative is that it is more severe, hence the greater than. Moving right along. Of course, just like in confidence intervals for proportions, we can use the calculator for hypothesis test for proportions. We go to our calculator, hit stat. That's going to bring us to this screen. You go to tests, and we don't have to go as far as alpha A. We go right to number 5, so you can scroll down and hit 5, or just hit the number 5. Brings us to this screen. We're in a 1 proportion z-test. I have the wrong information on this screen, though, unfortunately. I'll correct it on the fly. This is going to be 0.28. That was the null hypothesis. Our x value, now notice this is why I spent so much time on it before. Our x value must be an integer value, so we can't put that 304 and change. We got to put 305, and then this is 801. It is still greater than the null, and we're going to hit calculate as the word sitting there. And then we get here, and our values are 6.35. It goes further than that. And then this is that long 1.066 blah, blah, blah times 10 to the negative 10. It actually doesn't say 10 to the negative 10. It says e to the negative 10. And then our p hat is 0.38 and change. And our n is 801. But the gist of it is that the calculator reports it. Sorry about that mistake. And then if you were to go here and choose draw instead, it would give you this scenario, and then the your z-stat value would be right here again, 6.35, and your p is the p-value, and again it would be 1.066 change e to the negative 10. So calculate gives you this picture, draw gives you this picture. I prefer the calculate piece. I should have already drawn a picture. The only thing I get out of the drawing is verification that I drew the right picture. They should agree at least. If they don't, well then I think I drew the wrong picture or selected the wrong command. And the last thing I want to draw attention to here is that which alternative hypothesis I chose here had to do with my original alternative hypothesis at the beginning. And that'll about wrap it up for hypothesis test for proportions. See you next time.